talk about control theory a little bit. This is the sort of the last third, if you will, of the course where we're going to talk about how to make these systems that we've been analyzing all this time do what we want them to do. So if you think about design of an engineering system, and now we are, like we're doing it, right? This is our project. It's not just to analyze the system, but to design a system. The analysis is a great tool, and it's really necessary to do real engineering design. But we want to go beyond just analyzing a system, and we want to start making it do what we want. Now, you can do that through choosing parameters to be a certain way. So say you did some system analysis on some product that you're building, and you could simulate what it's going to do. You could predict it. And you could say size different parts accordingly so that you got the performance you were desiring. You could choose the parameters, you could choose the material properties according to what your analysis says they need to be in order to get the performance that you want, right? Now that's one way to go with design, and that's going to be a big part of every design, is knowing through analysis what things are going to do, and choosing your materials and your geometry, etc., accordingly. Now, sometimes that's not enough. Okay, sometimes it's not enough to just have a system that you choose all the right material properties and all that, and it just performs how you want. And those situations arise actually quite a bit when we want to automate something. We want something to happen automatically. Sometimes you can design a very passive system that doesn't require control, but oftentimes we need some sort of control on the system. So that is the topic that we're going to discuss in the last third of this. How are we going to control how the system behaves? Okay? And the system is going to be the same system, same sort of system that we've been analyzing for a long time. Lumped parameter model, very common. We can do a pretty good job of modeling lots of different systems now. We've talked about mechanical, translational, rotational, electronic systems, fluid systems, thermal systems. And all of those different energy domains, they all arise in our designs all the time. So the design that we're using for our project uses two of those energy domains. Which two are we using? Yeah, well, actually, I guess there's three, really. This is mechanical, thermal, and electrical. Mechanical, not as much, in the sense that there's not a lot of dynamic mechanical things going on. We might have to do a little bit of dynamic analysis, potentially on if there was like a door that was hinged or something like that. It's moving. We might have to do something, but most likely we won't be too worried about that. If you wanted to make a really nice hinged door on it, then you would want it to be damped a little bit so that it doesn't slam. You guys are all familiar with slamming doors, and if you put a damper on them, they're so much nicer to deal with. It's the same. They started doing this with drawers now too, and cupboards. Like, it's really nice. I remember the first time I was in the kitchen. Really? Ah, that's nice. Yeah, see, it's like those little things that are really great. But yeah, like my cupboards just wham, they slam shut, and Same with my drawers and everything. So it's nice to have that little like buffer. It doesn't slam. But most likely we don't have to do a lot of mechanical analysis on this. So dynamic analysis. We might need to do, we could possibly do some stress analysis on it. It's not going to be a lot of stresses, but depending on how we decide to put this thing together, there could be, we would like to say, okay, well, maybe we can get away with this way of attaching things, but we might need to do a little bit of analysis to make sure that's okay. So we might do that, but as far as dynamic analysis goes, not a lot of mechanical analysis in this project. But electronics, yes, and thermal, for sure, yeah? So most likely we're going to get that thermal energy from a conversion from electrical energy, right? Unless you guys want to put like some radioactive isotope in there that's like warming. I don't know. Yeah. Probably not what we're going to do. I just watched... We're doing that now, yeah. I just watched The Martian last night. Never mind. I don't want to give it away. Have you guys seen it? Yeah.
I've read the book.
Yeah, okay, cool. So everybody knows the idea. He lives on Mars. He becomes a Martian, right? But yeah, he definitely uses radioactive material to stay warm, which they did in Russia back in the day, and before they knew that it was going to be really bad for people. I think, giving them the benefit of the doubt, they knew it wasn't going to be bad. They did it not for the people, but for the livestock, I think. They kept them warm with radioactive material. Not good, as it turns out.
Rum also keeps you warm, but anyways.
What does?
I said rum.
Rum also, yeah. I don't know if it's actually keeping you warm, but it feels better, I think. Okay, so we have these different domains that we can analyze, right? And like our project, and we can write up a model for them. We can predict how they're going to behave, and so we can choose materials based on that. We can make decisions in our design based on that, which is a big part of what we're going to do. But we can also specifically control different parameters. And this is another thing we're going to want to do in our project. What is the thing that we want to control in our project? Temperature. The temperature, ideally, of the kefir, right? But most likely we're not going to have a direct measurement of that temperature. It's hard. We could dip a thermometer in, but it's getting messy because somebody came by my office earlier, which was nice, and clarified. We're not going to be having the kefir sit in this apparatus without a jar. So it's going to be in a jar. It's not going to be pour it into this machine. The reason for that, there are several reasons for that. The main reason for that is that I don't want you guys to have to worry about the materials that you need to use with food versus not with food too much. And obviously it should be relatively safe, not really bad radioactive material. But I also don't want to have you guys have to worry too much about making it perfectly sealed and all of that, which is hard. It's doable, but it's harder that way. So it should be able to, however, be spilled on and not go up and smoke. So that's something. It should be able to be spilled on. If it's gonna be in the kitchen, it's got to be able to be spilled on a little bit, to a point. Obviously, it is not going to be perfectly sealed. But we are going to have a measurement of the temperature, probably of the air in the chamber, and we want to control that, right, to be a certain thing. So say I want it to be at 70 degrees Fahrenheit. That's our set point. That's what we want it to be at. And that task we will learn how to perform in this last 6 weeks of class, essentially. We're going to learn how to control some parameter in a system, or some variable in a system. And that, it's actually, on like a basic level, intuitive level, it's pretty easy to think about, right? Like, okay, I want this to be 70 degrees, and I have like a heater / cooler, and I can heat it up or cool it to be that. And on a basic level, we think, oh, like a thermostat, it's gonna kick on if the temperature gets below that until it gets to the temperature we want, and then, or if it's air conditioning, it's going to cool down to that temperature, turn off then. And that is like, that's one way people do control. That's a very basic way of doing control. But you can't do very complex things with that method, okay? It only works for the most basic systems, and the performance of that is not great. So control theory is a big topic of like, how can we do better? How can we control these variables? Like for instance, how can we make the temperature get to the set temperature in less than 5 minutes? Like maybe it's okay if it takes 5 minutes, but it's not okay if it takes 5 hours. How do we make it get to the set temperature exactly, and not maybe exactly, but within, say, half a degree, given that a lot of dynamic systems, when they respond, they have some sort of error. So a lot of feedback control systems have steady state error, they call it. So even when it settles down to the new temperature, say it's set at 70, it might settle down to like 68 or 72, and it won't close that gap. How do you fix that? So that's another concern that we have. And then finally, you can have some systems that once you start using control on them, feedback control on them, they become unstable for certain situations. And so we want that to not happen too. So those are different considerations that, so if it became unstable, for instance, like it would heat off to infinity. It's really hard to make a thermal system unstable, however, but it's possible. The performance considerations like that are why control theory is a thing. And it's a big thing, and there are lots of techniques in control theory, and it's a really cool topic. It's one of the most recent developments in your engineering curriculum. It mostly was developed primarily in the middle of the 20th century, in the 40s through the 70s, I guess, was like the heyday of it, which is much more recent than most of the topics you guys have learned about. And it's kind of it has sort of another renaissance recently because of computers, right? So we can do a lot more with control systems now that we have wide access to cheap computing. Whereas when they're first doing it, it was brought on, I mean, it's power came around the same time as computing technology, but it was expensive and only applied to they only could afford to do stuff on like rockets and things like that. But now you could do it on just a little device in the kitchen or whatever. Like it's cheap. You can do it for practically free. It's very, very inexpensive to buy the hardware now. So, okay. So I'll kind of go through this set of notes a little bit, and we will get a sort of flavor for what we're going to be doing. So, control theory is the study of control systems that control the behavior of other systems, okay? So when you have a controller on there, then it controls the original system, or sometimes called the plant. So this means that control theory is fundamentally about design as opposed to analysis, like system dynamics is about analysis. So in control theory, a system, usually called the plant, is analyzed, often with system dynamics. Then a control system is designed to control the plant. Control system usually controls the plant by changing one or more of the plant's inputs. The plant's outputs are variables we would like to know and or control. So remember, in system dynamics, we've been talking about how a system has inputs and has outputs, right? And up to this point, we've just said, oh, inputs, they're just specified. They're always given, or, whatever. They come from the problem that's given to you, or maybe the situation says, okay, this is the type of input you have, like it's a motor and it's a sinusoidal input. Okay. But in control systems, we say, oh, those inputs, we can actually specify those inputs. We can choose what those inputs are going to be. And that's how we're going to control the system behavior. And the system behavior that we care about is in the outputs, right? So the outputs are what we want to control, and hopefully we have measurements of those outputs. We don't always, but ideally we have measurements of all the outputs that we care about. If a plant is mathematically modeled with sufficient accuracy, a controller can specify the plant's input, which is the controller output, to produce the desired plant output. This is called open loop control. So if you really know what's going on in the system, if you give it a certain input, then you're going to get a certain output, right? If you've modeled it well enough, you can just say, oh, okay, well, I'm going to put 4 volts in, and then this is going to happen. You can know. However, most plant models are not understood well enough to do this. Okay? Usually, we've put together a lumped parameter model like we like to do, drawn a linear graph. It might be, accurate to within 10%, something like that. That's not bad. But we probably can't get it a lot closer than that for a lot of cases, especially when there are things like disturbances from the outside, like some input that you don't know about is coming into the system and affecting it. So that's one of the big challenges of engineering, is what do you do when you got imperfect knowledge of what's happening out there. So for this reason, most control systems include feedback. Okay, so measurements of the plant's outputs are called feedback. These measurements are fed back to the controller, which determines its output, which is the plant's input, from this information. So we say, okay, I want the temperature in this chamber to be 70 Fahrenheit. Right now, it's 66. Therefore, my controller now needs to make a decision about what kind of input I want to put in. It's going to make that decision based on your controller design. So deciding what the controller is going to do when it finds out what the actual temperature is, given what you want it to be. Then you have to, the controller design is all about what do you do when you know what the error is, okay? So, determining how the controller should respond to the feedback to control the plant's output is subject to much of control theory. So is the subject of much of control theory. There are several types of controllers used in control theory. Which is best for a given system is the primary task of the control engineer. There are design trade-offs to be made. Some controllers will be more expensive to implement than others because they will require more expensive hardware. You can control things really well, but you have to pay a lot of money to control things really well. So the key is to always, just like with other design tasks, we want to accomplish the requirements, but just barely with minimal cost, right? Trying to be efficient about it. Some controllers will perform better than others in some aspects we will now explore. So here are the three aspects, and I mentioned them in passing before. The transient response is one of the performance characteristics. So there are three major performance characteristics: transient response, steady state response, and stability, okay? And that's actually what we're going to deal with first over the next couple weeks is how do we evaluate the performance of a controller? And then we're going to talk about how to design a controller, okay? So transient response is the first one we'll talk about. So it's the plant's output. So transient response of the plant's output is often important for a control system. So it's the response from when you specify the set point to be 70 degrees. It's how it goes from 66 to 70 degrees. That's the transient response. So designer may have identified such requirements as the velocity free response or initial condition response must be, say, 0 plus or minus 1 meters per second in 5 seconds and thereafter, for instance. Like that could be something that's required, and that's a transient response requirement. Like that has to be the case. Or the pressure step response must not overshoot its final value. That could be another one. This type of requirement is common. As with many design techniques, some iteration is usually needed in order to meet all of the requirements. So oftentimes we will design it based on some performance criteria, and we'll find that, it meets 2 of the 3. We're going to need to tweak it, and hopefully we can find some space where they're all met, okay? And that's sometimes challenging, but that's always what we're working with. So steady state response of the plant's output is another important consideration. After the transient response has decayed, the steady state response must meet certain criteria, such as the position steady state response to a unit ramp function must be within 5 millimeters of the desired position. That could be the requirement. So steady state is once it stopped the transient response, it's in steady state. So you can have an error in that. So you can have a control system, and a lot of them do. Like I said before, if you want to set it to 70 degrees, they might stop at 68 degrees, and it never gets closer. That's a steady state error, and we would want to try to mitigate that somehow. And finally, stability. A control system must be designed such that the plant's output response is stable. So its free response must eventually approach 0, or it must approach an oscillation with a constant amplitude, right? We could be marginally stable, that's fine. We don't want an unstable system for sure. We don't want something that's going to go off to infinity. And so that's these are all things that we've seen in our system dynamics discussions. We've seen stability, we've seen transient response, we've seen steady state response, but we haven't thought of them so much in terms of performance yet. And so now in control systems, we're thinking of those things as being performance metrics. And finally, of course, we have other considerations: cost, weight, complexity, and many other factors for a control system. One of the most important is robustness, okay? The control system's ability to perform as desired when system parameters change from their nominal values is robustness. So if it's a really robust system, it's a really robust controller design, you could be, you might say, in our case, say somebody put in, instead of putting in a quart size jar worth of kefir, if they put in like half a quart or a quarter of a quart, or maybe they put in, you could fit in there still like 2 quarts, like they stuck 2 quarts in. Would it be robust enough to still perform okay, or would it totally fail? So if it's very robust, it would still do okay. Might not be as good, but it would still do okay. If it's not robust, then it wouldn't be able to handle that. Okay, so feedback control, block diagrams. So we've seen block diagrams, and it may have seemed a little bit mysterious why we talked about block diagrams so much. We talked about, oh yeah, transfer function. It's good to think of it as a block diagram. Input going in, the output going out, right? Great, but this is really why we talked about block diagrams, is that control systems are almost universally represented as in block diagram form, okay? And this is where it becomes really useful and very powerful to use block diagram. So, a useful tool for designing control systems is a block diagram. The plant and the controller are represented as blocks, okay? And I'll label them on here. And I'm going to send you guys out these notes so that you have them. I couldn't get them printed out, so don't worry about that. There we go. So this is our plant. Oops. This is our plant, G. And so what we've done is we've analyzed our system, like our thermal system, our project this year is this thermal box, right? And then there's this electronic stuff going in. So we've done all that, linear graph, we've got maybe a state space model of it, and we found a transfer function from, say, the voltage input to the temperature, something like that. That would be one thing we could do. So our input to the system would be voltage, and our output would be temperature. So that would be represented in this block G. So this is Y, the output. G is the plant. We have the output of, so these are the inputs. I'm going to write U here as the input to the plant. And the output of the plant is Y. We feed that back, okay? What we say is we want Y to be some command. We'll call it R, okay? This is the command. So for instance, if this was the temperature, we want this to be 70 degrees. So that would be, R would be 70. It's actually, say, 66. We want it to be 70. This is a summing junction here. If we take R minus Y, we get the error, right? That is essentially the difference between what we want and what we have, the error. And so in this case, at this moment, the error would be what? 4. And we're going to hand that off to the controller. Okay, controller, we'll use C. We can use different, there are different labels here. It's not universally C, but sometimes it's called C. And we're going to represent that by a transfer function. So we're only really going to consider control in this class that can be implemented via a transfer function here. And this is where all the magic is. We have to choose the controller transfer function such that this output follows this command as closely as possible. The controller output, it's a little bit simplified because you're going to have probably some sort of actuation here, but maybe that's part of your plant. So oftentimes the controller output is just a voltage. But we always call this the control effort. The output of the controller and the input of the plant is the control effort. That's what you have to do as the control system to make the system do what you want. So obviously there's an expense. So if you want that output to follow the command really, really well, you're probably going to have to use more control effort. But there's always a trade-off between how much control effort you want to use or can use versus what you have available. So in this configuration, a command function R is provided, right? And we compare that to the actual output. You have the error, goes through the controller. Control effort goes into the plant, which goes to your output. So this is a constantly sort of updating, you can think of it as constantly updating cycle. Now, ideally our error is 0, of course, and what we're doing when we're designing control systems is we're trying to make that error 0 or as small as we want, as we need it to be, and as a function of time, of course, it has some response, so we have to choose our controller accordingly. So here's an example. It's really more than an example. It's more of a demonstration of how to find what's called the closed loop transfer function y over r. Okay. So what becomes immediately interesting is, say I want to make the temperature 70 and the temperature right now is 66. So how does the system respond when I set it suddenly to, so say it was not set to anything, the controller was off, or it was at 66, so we're not doing anything. And suddenly I say, okay, let's make that command, instead of 66, let's make it 70. How is the system going to respond to that dynamically? That's what we're going to need to figure out, and that can be determined by a transfer function, which we will now derive. What is the transfer function from R, the command, to Y, the output? So CG, but then there's this, so that's CG times E, right? But then you've got E is equal to R minus Y, but then you've got the answer in there. So it's a little bit of like, it's like a loop, but it is a loop. So what we're going to do is we're going to write down some algebraic expressions that we know, and I'll show you how to solve for that relationship. So first off, we could write an equation for the error, right? The error is R minus Y from the summing junction. So there's that expression. The control effort is C times E, right? It's the transfer function C of S hitting on the error, so CE. And then finally, we could say that the output Y, as this is the one we're most familiar with, right? Y is equal to GU, right? So Y is equal to GU. That just says that Y over U, the output over the input of the plant, is just the transfer function of the plant. We're really familiar with that one. We're also familiar with the fact that Y is equal to GU. So those are all expressions. Let's see if we can manipulate those expressions. Those are the only ones that are known in this diagram. And the diagram, all it's really doing is representing algebraic relationships, right? It's just saying, this diagram just says E equals R minus Y, U equals CE, and Y equals GU. So it's like 3 algebraic equations, or this block diagram, like either one. So let's use these 3 to solve for the closed loop transfer function Y over R. So let's start with this last one. So y of s equals g of s u of s. Yeah, so u of s is just equal to CE, so g of s is still there. Plug in that u is equal to c of s, e of s. Okay, but e of s is just equal to r minus y, right? So g of s, c of s times r minus, needed a of s, minus y of s. And we have used all three equations, which is a good sign. We were trying to eliminate from this these intermediate variables. Okay, we wanted to eliminate u, we wanted to eliminate e. What we want is to relate r and y via c and g only. Okay, and what we have is this version of the left-hand side, y of s, is equal to this version of the right-hand side, g, c, r minus y. And we've eliminated all of the variables that we needed to. So to get y by on the side by itself, we can add g, c, y to both sides. So we get y of s that remains on the left-hand side. We have to add it to both sides because this is a negative sign. So plus g of s, c of s, y of s equals, what's remaining on the right-hand side? G of s, c of s, and r of s. Good. So now we can factor out y, right? So y, and then we'll divide both sides by 1 plus gc. So y of s is now by itself, and we have g of s, c of s. I'm not going to write r of s. I will write in a second. Divided by what was factored out, or what was remaining after we factored out y. Yeah. And all that's multiplying r of s. And that allows us now to divide both sides by r, right? So we have y of s over r of s equals g of s, c of s divided by 1 plus g of s, c of s. All right, so there's our answer. That's the transfer function, the closed loop transfer function from the command input to the output. And that's actually, that little derivation is very fundamental to a lot of control theory because they all pretty much follow this format. You can have instead of the controller up here, you can have the controller down here. You might have a transfer function down here. Your measurement might not be of the temperature. It's probably instead going to be a voltage, right? And the voltage is probably going to have to be turned into some signal that you can turn into a temperature. And through some gain or via some instrumentation, you're going to have that measurement. So there might be a transfer function in this feedback loop. All of that stuff can happen, but essentially the same program can be followed, and you can write a closed loop transfer function from the command to the output. And that's always what we're interested in control theory. We're trying to make that relationship between the command and the output what we want. Notice that this closed loop transfer function depends on the plant and it depends on the controller. So this thing's going to have different properties associated with it that depend both on the plant and on the controller. And we need to choose those to respond accordingly. Okay? And that's what we will continue to discuss next time.